The next part of our discussion is going to focus on the classification and etiologies of hyponatremia. Hyponatremia can be classified both by tonicity and by volume status. With regards to tonicity, it can be either hypertonic, hypotonic, or isotonic. And by volume status, it can be classified as hypervolemic, hypovolemic, or euvolemic. So let's start by going over classification by tonicity. Hypertonic hyponatremia is defined by a depressed serum sodium concentration in the setting of an elevated serum tonicity greater than 290 milliosmoles per liter. And by far the most common cause of this is hyperglycemia. Because glucose is an osmotically active substance, when the serum glucose concentration is elevated, it pulls water out of cells into the extracellular compartment, thus depressing the serum sodium concentration. Notably, this is not what is meant by pseudohyponatremia, which is a different entity entirely that we'll touch on in a minute. We can actually quantify how much the sodium would be expected to drop for a given rise in glucose. For every 100 milligrams per deciliter increase in the serum glucose, the sodium is expected to fall by 1.6 milliequivalents per liter. So as an example, if we assume a normal glucose of 100, if a patient comes in with a glucose of 1100, we would expect the serum sodium concentration to fall by 16. And as you would expect, if you correct the glucose back to normal, the sodium should return to normal as well. Next is isotonic hyponatremia. And frankly, the biggest takeaway here is that isotonic hyponatremia is extremely uncommon with modern lab techniques. And unlike hyponatremia secondary to hyperglycemia, this is what is meant by the term pseudohyponatremia. It's caused by displacement of the water phase of plasma by non-hydrophilic substances, for example, severe hypertriglyceridemia or hyperproteinemia. Now we're devoting an entire slide to this topic, not because it's a particularly common etiology, but rather by going through the concept of pseudohyponatremia, it gives us an opportunity to review some useful physiology. So let's take a step back and review the normal components of plasma. In any given volume of plasma, about 93% is composed of water and substances dissolved in water, such as glucose and electrolytes. And the other 7% is composed primarily of larger, non-hydrophilic substances, such as fats and proteins. So how is this relevant? Here I'm going to draw some volume of plasma. I'm going to label this 93% as the water phase, and this 7% is the non-water phase. What's important to appreciate is that in any given volume of plasma, the entire content of sodium and of water is relegated to this 93%. There is no sodium and no water present in this 7%. So in fact, the concentration of sodium dissolved in water in any given volume of plasma is closer to 154 milliequivalents per liter, which is higher than what we typically consider normal, around 140. And this is because when plasma is analyzed in the lab, the sodium concentration is calculated by taking the amount of sodium present in the given volume of plasma, which is again relegated to only this 93%, and dividing it by the entire volume of plasma in the sample. And this is why we consider a sodium of closer to 140 to be normal, because the lab doesn't measure the sodium to water concentration, but rather the sodium concentration in this entire volume. Now the number 154 should sound familiar, and that's because it's the concentration of sodium in normal saline. So if you've ever wondered why normal saline contains sodium at a concentration of 154 milliequivalents per liter, it's because the true concentration of sodium dissolved in water in any given volume of plasma is closer to that. So what happens in pseudohyponatremia is that this non-hydrophilic portion of plasma is significantly expanded, due, for example, to severe hypertriglyceridemia or paraproteinemia. So now let's say we have our volume of plasma, but only 80% is the water phase because it's been displaced. And let's say a full 20% is made up of these non-hydrophilic substances. The sodium to water concentration is unchanged here. It's perfectly normal. But the sodium and water content in any given volume of this particular plasma is now decreased. And the volume that the lab is going to measure the sodium concentration in is this entire volume of plasma. Which is why in pseudohyponatremia, the sodium concentration is falsely low. And again, it's important to note that in this disorder, the sodium concentration in water is perfectly normal, which is why this is so different from hyponatremia secondary, for example, to hyperglycemia, in which the water phase of plasma is expanded and the sodium to water concentration is truly depressed. Moving on, let's talk about what you're much more likely to encounter, which is hypotonic hyponatremia, in which the measured plasma tonicity is less than 275. When classified by tonicity, this is by far the most common and what you're most likely to be faced with on the wards. And finally, in addition to tonicity, hyponatremia is also classified by volume status. It can be hypervolemic, euvolemic, or hypovolemic, with common etiologies outlined here, and we're going to go through each one in more detail in the next section.